You shall see. Thank you very much to the local organizers for having set up this, what promises to be a very good meeting. So I'm going to talk about chi-square statistics, and then I'm going to bore you with 3 proofs of the same simple fact, which you probably know already from your undergraduate degree, but just trying to make different points about how we can get chi-square approximation results using different techniques. This is started with a question by Percy Diaconis in 2000 about chi-square approximation, and then Alistair Pickett did a doctoral dissertation on it. Robert Gaunt helped to tidy it up, and with Andreas, we finally put in the part that we actually get chi-square approximations for Wilks' theorem, which is the pinnacle, in my view. So chi-square statistics, there's a quotation from a paper by Wing Wong and so Fan Hung and Wong. One of the most celebrated folklores in statistics is the theory of maximum likelihood ratio statistics. Under smoothness conditions, the null distribution of minus 2 log lambda, which is the log likelihood ratio, tends to a chi-square distribution as the sample size tends to infinity. And this is usually proven by using that the MLE is approximately normal under the respective conditions, and then using a multivariate normal approximation. And the questions are, first, is there a general bound on the rate of convergence? And secondly, chi-square approximations may hold when there is no underlying normality. So there's a case for developing Stein's method for chi-square approximation. So here's my view on Stein's method, and most of you know Stein's method very well, but just for those who don't, just a quick recap. So it all started out with Stein's paper, which he published in 1972, that Z is standard normal if and only if for all smooth functions f, expectation f prime of z equals expectation z f of z. That actually appeared in Peter's talk in a bit of a hidden way. So with this characterization, which just follows by integration by parts, we can then solve the Stein equation. So we pick a function h, and we look at h of x minus nh, where nh is the standard normal expectation of h, and equal it to f prime of x minus x f of x. And then we can replace x by w and take expectations, and therefore for all smooth functions h, we then have expectation h of w minus its expectation under the standard normal distribution is expectation f prime of w minus expectation w f of w. Why? So this is what I used to ask Charles. Why do you set up the Stein equation? And his answer was usually just to show me another example why it works. So despite of this fundamental question of why, which is I'm still battling with, and every new Stein equation that I see, I try to fit into my current state of mind. Stein's method has been extended to many other distributions. Of course, Louis Chen worked on the Poisson distribution, multivariate normal, Andrew Barber, that's a compound Poisson, William Lowe, binomial aim gamma, which was Ho-Ming Luk, student of Larry's, the beta distribution, we did actually should have added Doppler variance gamma, Robert Gaunt, Laplace, Pike and Wen, Dickman, not on the list anymore because there was only one space there. So there are more. Well, that's a female excuse, but so there are many more distributions where you can set this up. So generally, we have a target distribution with some support, and we want to find first a suitable operator and a wide class of functions such that access the target distribution if and only if for all functions f in this wide class of functions, expectation af of x is equal to 0. So this operator acts on the distributions through these functions f such that the expectation of it would be 0 if x has the true distribution mu. And then we set up a Stein equation. We take again a test function h, and we write h of x minus this expectation h of x, capital X, is a f of x. We solve that, and then we can, if we find a solution f, which might not always be easy, then we can replace x by any random element w, and we have expectation h of w minus expectation h of x is the expectation af of w. Now, how to find such operators is there are many different approaches. I'm not going to talk about that. The one which we found for the chi-squared using different approaches is x f double prime of x plus a half p minus x f prime of x. So this one works. Actually, this goes back to Luke, who did the gamma distribution in his doctoral dissertation. And so for any random variable w, we can just use this chi-square equation, plug in w for x, take expectations. So expectation h of w minus the chi-square expectation is expectation w f double prime of w plus a half expectation of p minus w f prime of w. So, so that you don't forget, I just put the equation in the title. So and we can bound the Stein equation, and actually bounding the Stein equation took several iterations until we came up with one which I actually, I forgot a parenthesis here. So if h is bounded and has three bounded derivatives, then the Stein equation has a solution f which satisfies that it's bounded by the k minus first and k minus second derivatives of g. And this is always the subnorm, divided by 4, multiplied by 4 divided by p plus k minus 1. So k is just the derivative, and p is the degrees of freedom. So that actually plays in your favor. So, yes, that should be h, yes. Yes. So now come 3 proofs of a simple fact. If you have the sum of IID mean 0, variance 1 random variables which have existing 8th moment, and we take the scaled sum of the xi's, so divide by 1 over root n, and take w is equal to s squared, then w will not be far away from a chi-square 1 distribution. So this is a fact which you probably will have seen before. And indeed, some time ago, I proved this bound. It's a 1 on n bound, so order 1 on n. We have the 8th moment of x, and we multiply by 428 plus 2,375 expectation of x cubed times the sum of the derivatives of the test function h. And that's, let me just find a pen. So if x has third moment 0, then the constant would be 428 for the chi-square 1. So this is a sketch of the first proof. So remember the chi-square equation up there? So I multiply with a half, so I want 2 expectation w f double prime of w plus a half plus expectation 1 minus w f prime of w. Want to bound that? Well, in this proof, the trick was to say something like Peter did in his talk just now. We put g of s as s times f prime of s squared. Then g prime of s is f prime of s squared plus a half s squared f double prime of s squared. So if I take s squared as w, s squared as w, then I can rewrite the chi-square equation as expectation g prime of s minus expectation s g of s. And then we can proceed as in standard normal. But I'd like to point out that this function g of s is s f prime of s squared is antisymmetric. right? So it's because s squared is a symmetric function. If I multiply f of s, any function f of s squared will be a symmetric function, s times f of s squared will be antisymmetric. And so, like in the normal, we use Taylor expansion, we expand around xi, so we take xi out of the sum, then the sum si is independent of xi. So we first write down g of s, take out si, we have a remainder term, and this one is expectation g prime of s plus two remainder terms. Now for the normal approximation, this gives you a 1 on root n bound very straightforwardly, but because g is antisymmetric and its second derivative is antisymmetric, we have for standard normal the expectation of g of the second derivative would be 0, and so therefore if you look at the remainder terms of the second derivative of w would themselves be of order 1 on root n for some constant f. So this is again using normal approximation, and then it turns out that the remainder terms, which usually are just of order 1 on root n, this way become of order 1 on n, and so this gives the 1 on n. And this is of course an explicit constant, which I did show you in the proof. And we applied this to Pearson's chi-square statistic. So Pearson's chi-square, we have n balls which are thrown into m boxes independently. Pi is the probability that x is in box I. Ui is the number of balls in box I. And then I look at the number of balls minus the expected number of balls squared, so npi squared, divided by the expected number of balls. I sum this up over all cells, and this would be approximately chi-squared distributed with n minus 1 degrees of freedom as n goes to infinity. And you may have learned in your undergraduate course, or you may even teach in your undergraduate course, that this approximation is good if NPI is larger than 5 for at least 80% of the cells, or something of that order. So that, I can show you, you can actually be much more precise in your lectures. So using this approach, we do get an overall bound, an explicit bound of order 1 over n, where the cell probabilities appear here as 1 over pj summed up squared. And so you can relate this to how good your approximation should be. Unfortunately, the constants are not fantastic. They are, yeah, so if you were to go yes, for this bound to be small, but the dependence in the PJs is that this term overall should not be too large. So if that's the question you're interested in. Okay, so of course this theorem applies for all n, so that's nice. The dependence on n is optimal in the order, not in the constant. The numerical constants are probably not optimal. I think we can show they're not optimal. So this was the first proof. The key argument in the proof is that this function t of s is equal to s squared is symmetric. And so any function of it is also symmetric. So g of s is s prime of s squared is antisymmetric. So more generally, we can consider test functions h of t, where t is a symmetric function. And then we can use a multivariate normal approximation as follows. So this is Götz's version of the multivariate normal approximation, Stein's method for multivariate normal. You have a continuous function Rd to R, and that is a standard d-dimensional normal. Sigma is non-negative definite, and then we've got a multivariate normal Stein equation with the test function h. Okay, this is slightly adapted, so I would say h of t of dot. So we think of w of, so s squared is the sum of the xi squared. in some scaling. So this would be our function t of s. And we can set up the Stein equation. So this is the second derivative with the covariance matrix sigma. So delta is the gradient operator. So this form is gradient operator transpose sigma gradient operator f minus w transposed gradient f. So this is the same as sigma squared f double prime minus x f prime, if you're looking in the univariate case, is h of, then I'll write a t of w minus h of t of sigma half z, which is the appropriately scaled normal. And so we can bound, and using Stein's method, we can bound this distance by solving this multivariate Stein equation for f and then bounding this part here. Now, Peter has already showed solutions of Stein equations which depend on the test function h. But if even if the test function h is Lipschitz, because now here we've got the function h of h composed with t, and if t of x, t of s is s squared, say, that's not a bounded function. So when you take a derivative, you don't get a bounded, so you don't get a uniform bound on these test functions. Well, not to worry, as we shall see, because in Stein's method we don't actually need uniform bounds; they are just convenient. So here's again our example with the w is equal to s squared. Write this. Squared. So I can think of w being a function of x1 up to xn, the function t of x1 up to xn, which just gives 1 on n times the sum of the xi squared, right? So that's a simple function which takes a vector from Rn into the real numbers. And I can look at the partial derivatives. Well, the first partial derivatives are clearly not bounded, but all the other derivatives are bounded, higher derivatives are bounded. And so when we look at the Stein equation, if we have a test function t such that, these derivatives, the partial derivatives, kth partial derivatives, this is to the power m over k is bounded by a polynomial p of w, which is of this form, then we can bound the solution of the Stein equation also and it's a non-uniform bound using the polynomials from the polynomial p, the coefficients from p which we've used here. And so here we've got w, and the components of wi appear here in the bound. So it's not a uniform bound, but it's a bound which just keeps the wi in. But that just means when you look at your remainder terms, you get this additional factor. So it's so this is a bit hand-wavy, but we can still get a bound, and we can also easily generalize this to local dependence, of course, as we did for the Pearson. So we take xij write myself, I is equal to 1 up to n, and j is equal to 1 up to d. So this is an array of random variables where we think that for fixed j's, the observations are independent, but for any fixed I, they may be dependent. So for each I, we observe a d vector, which may consist of dependent observations. And then wj is the sum of the xij, and then w is the vector, just the vector of w1 up to wd. And it's got covariance matrix sigma. So this is slightly different W because this would be a function. And then we can take any symmetric function and get a bound on the distance between T of W and T of sigma half Z, which would in our case then be the chi-squared, which is of this, this form where C1 and P and C2 of P depend on the polynomials. Now I have to look out my little paper. So this was the bound. This was the first proof, just assuming that the third moment vanishes, otherwise the bound is larger. So for the second proof, if I apply this to our simple problem, then we get a 30,720 divided by n. So we can do it, and I mean we can treat the Pearson case, but more generally we can treat a power divergence family. Power divergence family is like the Pearson, so we can have the multinomial vector of the observed counts, and assume that every count has expectation at least 1. Then the power divergence statistic in this lambda is this object here. So lambda equal 1 gives Pearson, but we can also use other lambdas. And then it's known that these power law divergence families are asymptotically chi-square distributed with r minus 1 degrees of freedom for all lambda. And again, we get an explicit 1 on n bound. And here we use that this T lambda is the sum of squares plus a second term which is small. So it's small in expectation. So it has to be bounded. So it's a bit of a perturbation approach. And that brings us to the third proof. So the first two proofs both went back to the normal approximation, right? And I said in the introduction, there are cases where chi-square approximation holds, but you don't have underlying normality. So using normal arguments seems to be somewhat morally wrong, although not mathematically incorrect. And so here's a proof where we don't have any recourse to normal. So let's assume that for some reason I call this axis now Z, that we've again got an array of independent mean zero variance 1 random variables, the same distribution, and assume that all mixed moments for order up to 8 exist. And I also assume here in the simple example that they are independent. So then I can write T, which is the sum of these squares as Z transposed Z as a quadratic form. The expectation is R, which is the degrees of freedom we want to approximate with, and T is also the sum of locally dependent summands. Right? So if I look at these summands, so the Zij, Zil, so they're locally dependent if we are in the block design framework. We can also make them independent. But so here we can take out everything that depends on the J's vector, and so we saw more where S not equal to J, T not equal to J. So it's very similar to the first proof, where we took out everything that depended on I. Only here we do it directly on the square rather than going back to the normal approximation. And then again, we can do the Stein's method explicit expansion for the Stein equation. And so I just put in what T is. So in the first part here, and then you see Zi, J, Zil, and I've got Tj here, f prime of Tj. Well, this is almost independent. and the mean of t is r. So this is our expectation of prime of t plus a remainder term. And so this term here we're going to look at soon. R1 is the remainder term from a first order Taylor expansion here. So expansion around Tj. And then again, so T minus Tj we can write down explicitly. And if we do this, we have two terms. So the first term here, Zij, Zil, that's squared Kj, f double prime of Tj. Well, there says some j's in there, but most of these terms actually will be zero because of the independence assumption. So the only terms which are not zero is when j is equal to L, so that's the only case. So we only have got one contribution out of n contributions, so that will be small. And this one here, again, so we have the Tj here, so what's j here is approximately independent, so you can just about squirt and think, oh, that's just a t. So this actually compares with the t coming from the other part of the Stein equation. So this and if we do this proof correctly, so we get a bound out. Actually, should just say the approximations can be quantified. So this is just hand waving again what I just said. So this proof, of course, generalizes to quadratic forms. So if I have, so quadratic form means T is Z transpose UZ, where U is some square matrix. So we think that we are, again, in this framework, that we've got independent vectors of observations, and we assume that mixed moments up to order 8 exist. And then Zi is the standard normal scaling of the sum of the Zij, and Z is the whole vector Z1 up to Zr transposed. And 2 is the covariance matrix, and we assume that it's invertible, and we call the inverse U. And T is Z transpose U Z, this form. And then with this, with the same approach that I just showed you, you can get a chi-square approximation, which has an explicit remainder term. And here I got the approximation of order 1 on root n. I haven't written down the approximation for 1 on n yet. It should also work, but it won't be in this paper where the rest appears. But I can show you. So for the same example, the leading term is of order 80 divided by square root of n. So you can compare which one is the better bound. So what we actually wanted to do all along is to look at the log likelihood ratio statistics and fit this in this framework. So log likelihood ratio statistics. So assume we've got IRD observations from a distribution. Assume it's got a smooth probability density function which depends on a parameter theta, which sits in RD. It's a d-dimensional parameter vector. And we want to test the null hypothesis that theta is 0 on the first R elements of the theta vector against the general alternative that theta is in the parameter space. So I'm not going to write down all the assumptions, the regularity assumptions you will have to make. I would just say this holds under regularity. So the parameter space theta has to be nice. The parameter is not allowed to lie on the boundary of the parameter space. And so we assume that the dimension of the parameter space is D. So it's not only a subset of RD, we assume that the dimension is D. And theta naught then has dimension D minus R. So I can write, I write my theta vectors as the first R component and then the R plus 1 up to D components. And the null hypothesis would then say that the first R components of theta are 0. So L of theta x is the likelihood function. And we assume that the maximum likelihood estimator exists, is unique, and having derivatives up to third order with respect to theta, so that we have nice analytic properties. And then we estimate theta under the null hypothesis, which is theta hat res. And we estimate theta under the general alternative, which is just theta hat n. And so the theta hat res estimating under the null, but we do keep the first R components, just write them as 0. The log likelihood ratio statistic is then twice the log of the likelihood under the full model divided by the likelihood under the null hypothesis model. And for convenience, I write it in a slightly awkward form by dividing by the likelihood under the true parameter in both cases. So that just cancels out. So theta naught is the unknown parameter. We need a little bit of notation. So we've got the Fisher information matrix, which I write with components A, B, B transpose C. And the score function is the derivative of the log likelihood. And I write this as scaling lie squared of n times the vector xi and the vector eta. And these are column vectors. And everything is so regular so that the covariance matrix of the score function is n times the Fisher information matrix. And little l is the log likelihood, as usual. And so the log likelihood can be written as the sum of the likelihoods of the log likelihood of the individual observations. And these are actually, these form IID vectors of possibly dependent entries. So morally, the whole argument, the key argument for the log likelihood ratio relies on these, and if x is random, then these are sums of independent random variables, or in our case, locally dependent random variables. So we've got a law of large number, we've got a central limit theorem for this sum. So the heuristic for Wilks' theorem is as follows. So we can do Taylor expansion for each of the log likelihood ratios for each of the log likelihood. So this is, so T1 is the likelihood under theta at n x divided by the likelihood of theta 0 x. So this is the likelihood ratio of just testing the null hypothesis theta is equal to theta 0, whereas we don't know theta 0. So we can do a Taylor expansion, and so you see this gives the maximum likelihood estimator theta hat minus theta naught transpose times the Fisher information times theta hat n minus theta naught. And also by Taylor expansion, we can expand the score function, also depending on the Fisher information. So we can put in one in the other. And so I can rearrange to get twice the log of T1. It's approximately psi and eta transpose times I of theta naught minus 1 psi and eta, where psi and eta don't depend on the maximum likelihood estimates anymore. And the Fisher information matrix comes in here. So if we don't, so the complication in the log likelihood ratio statistic comes from actually estimating the parameters, something we didn't do in the Pearson case. So the maximum likelihood estimator is what messes things up. But here with Taylor expansion, we can sort of expand it away for now. Of course, we have to bound the remainder terms that appear. But morally, this is how it looks like. And morally, we can have a similar expansion for log T2, which is just the one under the null hypothesis. Under the null hypothesis, only the lower right-hand corner of the Fisher information matrix enters, which is C. And so if I got twice log T2 is like eta transpose C minus 1 eta. So if I then look at the minus twice the log likelihood ratio, I can expand this out. This is the term from twice log T1. This is the term from twice log T2. And this is the approximation. And I can write this as Z transpose 2 minus 1 Z, with tau is related to the Fisher information matrix through this. And the Zij have a slightly complicated form, but we can write it out explicitly. And of course, we have the independence between the vectors, which sort of filters down to the Zij. And so we are now in this quadratic form regime, and we can get an explicit, so we can apply the chi-square approximation for quadratic forms, and we get an explicit bound on the distance to chi-squared for the log likelihood ratio. And so there's the term here which comes from the chi-square approximation, and this term here, S of theta 0, S just means the remainder term, it's not the score function. It's bad notation. So that second term just relates to the approximation of the maximum likelihood estimator by theta naught. And so Andreas Anastasiou wrote his doctoral dissertation on Stein's method in maximum likelihood estimation. So we wrote a paper on it, and he wrote a second paper on it. And for our proof here, we use similar ideas. We don't actually use the results from that paper, but we use the same truncation argument. And so what's also nice is that, so we've got a d-dimensional test problem here. So if we fix d, the bound is of order 1 over square root of n. And because for the maximum likelihood, we couldn't get anything better than 1 over square root of n, we didn't try very hard for the chi-square part, because that seemed to be not belonging in that paper. If d is not fixed and r is not fixed, then the overall order of the bound is of order d to the 23 over 2 over square root of n. So that means the chi-square approximation is justified when d is a little o of n to the 1 over 23. So that's not, I will talk about that in a minute, but maybe it's not a great dependence on n, but it shows that d can actually grow with n and r can grow with n. And so we can apply this to settings where we've got large data sets. We repeatedly invoke the Cauchy-Schwarz inequality for the proof, so we don't think that these orders are actually tight. And actually, we know in one example that they are not tight, which is the example of logistic regression. So logistic regression means that you have IID observations, so xi's are vectors in RD, and yi's is a binary outcome, so it's 0, 1, and we relate them to this regression model, the probability that yi is 1 given the explanatory variables x is 1 over 1 plus e to the minus theta transpose x, for theta is in RD. And we can test just a simple test that theta naught is identically 0 against the general alternative. That has been treated in a paper by Sir, Chen and Candace in 2070. They actually show when d grows as fast as n, then the chi-square approximation no longer holds. So we have got d to the 1, like n over 1 over 23. That's certainly below d is equal to n, but we cannot assume that if d is larger than n, that the chi-square approximation would hold. And that makes sense. They actually give a correction term to make things still work out. And Portnoy in 1988 already showed that a chi-square approximation is valid for logistic regression when d is a little o of n to the 2/3. We are far away from 2/3. And so, but we've got an explicit bound, so Portnoy does not have an explicit bound. And actually our explicit bound is, so in some examples it's not so bad. And just a bit about related work. So quadratic forms have of course been studied by many people. Kötze, Bielefeld, one of the people working a lot on it, Kötze and Tikomirov, showed a 1 on n bound in Kolmogorov distance, but not explicit. So for Pearson's statistic, there's a paper by Brad Mann, which I'm not sure ever appeared, but he worked with Pearson. He had an explicit order 1 on root n bound in Kolmogorov distance. Götze and Ulyanov have a non-explicit order 1 on n bound when R is bigger or equal to 5 number of cells. For Bauer divergence statistics, Ulyanov and Zuboff, so more generally, have a bound of order n to the r minus 1 over r, so not quite 1 on n in Kolmogorov distance for r bigger equal to 4. And there's a second paper by Asilbekov, Ulyanov, and Zuboff, which gives a bound for r equal to 3 as well, which is also not quite 1 on n. And they use arguments from number theory and from differential geometry. So very, very different to our group. And then there's, of course, related Stein-Maljavan calculus. So you can also give chi-square approximations. Actually, with Ivan and Giovanni, written a paper about 10 years ago about universality for homogeneous sums, where we have a chi-square approximation for homogeneous sums. Nodin and Poli have Maljavan calculus for the second Wiener chaos, which is related, so it's chi-squared minus 1. Invariance principles also Atzmode, Beccati, and Poli have worked on it, and more generally Stein characterizations for centered random variables which live in a finite sum of Wiener chaoses more generally, been studied by Arras, who's here, Atzmode is not here, Poli is here, and Swan is here. So people have been have done work in this area using Maljavan Stein, but they have not. So none of this work considers log likelihood ratio statistics because of the issue of estimating the parameter theta. So just one thing I would like to end with. In the 1972 paper, which started it all, by Charles Stein, he wrote, "I regret that in order to complete this paper in time for publication, I've been forced to submit it with many defects remaining." So, I think there's, yeah, so I think sometimes it's good to publish things even when you think they're not perfect. Okay, thank you for your attention. I don't think anybody can complain about me not looking favorably on Stein's method papers, but there might be the odd suggestions about improvements. Mm-hmm. Well, so we need to estimate up to 8 moments. for the bounds in the end. So yes. So yeah, yeah. Yes. 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 But we did observe that problem in the proof. So I represent it here as we just assume that it is the same. So, but yes, there's an issue which we have not really addressed. There's actually a trick which we use for the normal approximation for the maximum likelihood estimator, is that we can estimate the mean square error using the bound from the Stein equation. So using the bound from Stein's method. So in the normal approximation, the mean square error appears as part of the bound, but the mean square error itself we can then approximate again using the bound, using iterative procedure. So there might be something that could be done in order to ameliorate that. But yes, sometimes the statistic might just not. And the Wilks theorem is, so yeah. Yes, or something like, might pass the question on to Peter, the mod Gaussian convergence. Yes. And also, the likelihood ratio might not always be the best way of testing, of course. So it's really something that I think is a cornerstone in statistics, and you want to know how it behaves. But in real application problems, you might need to tweak it. So it might not be what you want to use in graduate statistics, if you like. So. Thank you.